As we noted in the introduction, we'll focus on really two broad types of meters. The first being positive displacement meters. Displacement type meters are typically going to be used for lower flow applications. We'll use them a lot for especially our billing uses as opposed to the big production meters we might see at pump stations or reservoirs or treatment plants. They are in that flow range, and the appropriate flow range for those meters can be highly accurate, but that accuracy can change over the life of the meter, so we got to be careful about that. The primary types of positive displacement meters that you might see in the distribution system are referred to as nutating disc meters or piston meters. For the rest of this discussion, we're going to focus on the nutating disc, but keep in mind that both of those are types of displacement meters that you might find. Nutating disc meters are very common for water agency billing meters. They measure essentially all the water that passes through the meter, all the water that passes through the disc. The volume in each cycle is constant. So you're measuring a known volume passing through a measuring chamber. So as you can see in the exhibit, you've got the disc assembly, and as the water goes through, it causes that disc to rotate, and every cycle of rotation of that disc is equivalent to a known amount of water. So the volume displaced in each cycle is constant, and the registration of the water usage is based on the number of cycles. And every time that disc turns, that's a cycle. That's a certain amount of water. It's a known volume that goes through the meter. So every time it turns, you are ticking on the register, and that's how it's quantifying the amount of water that goes through it. You have essentially a rotary motion of that tilted disc. That's how the water passes through the chamber, the metering chamber, which again, the important thing here is, much like we talked about with pumping applications, where you're pumping the entire volume of a pumping chamber, in that case, that it was a kind of constant as you cycle through it. In this case, it's basically the same concept. You have a constant volume that as it goes through, you rotate the disc and you're reading the meter, ultimately generating a read on the meter. They're used for design, at least for relatively continuous operation. The goal is that they are operated typically around 50% of their maximum capacity. Using continuous flows at the maximum capacity of the meter will damage the meter. It'll cause it to wear sooner than it should and can contribute to significant accuracy issues. So the maximum flow rates are going to vary based on the size of the meter. For a 5/8 inch meter, a really small billing meter, the maximum flow is around 20 gallons per minute. And that goes up at 3/4 to 30 gallons a minute. At 1 inch, it's around 50. At 1.5 inches, it's around 100. And at 2 inches, it's around 160 gallons per minute. So you're going to range in that 5/8 inch to 2 inch size from about 20 gallons per meter to 160 gallons per meter as far as its maximum capacity. And then keep in mind that typically we want to operate these meters at somewhere around half of their maximum capacity in order to not overly stress or wear the meter. So when operated properly, these meters are very accurate at flow rates up as you go up to the 2-inch meter size. You will have relatively higher head loss at high flows, and if you look at the assembly, you see that it's got to push that disc around. So yeah, there's some obstructions in the flow path. But again, you take that into account as the meter is designed and sized. The higher the flow and the smaller the meter, you're obviously going to have more head losses. So these types of meters are typical for residential and small to medium commercial applications in that 5/8 inch to 2 inch size range. Again, most of the water meters in a distribution system are positive displacement meters, and the nutating disc design is a very common application. We do have to keep in mind, as I said though, that the meters have to be designed properly. A small meter and large flows, you're going to have head loss issues. A large meter with smaller flows, and you're going to have potential accuracy issues. These meters don't typically over-register. They don't usually read more than what water passed through it. Again, if you think about the concept, they're only reading the volume that went through it, and it's based on that known volume of the chamber, so it's very difficult for it to read more. It's going to read how many times that disc turns, and the disc only turns when the water goes through it. What can happen, though, is you can get some under registration, as you can get at low flows water that's sneaking through the meter without really turning the disc appropriately. So that the typical error with these type of meters and the typical accuracy issue is going to be under registering and under recording of the amount of water. So you're actually reading less than the water actually that goes through the meter. That's obviously of concern given that these meters are generating revenue. I'm dealing with an issue right now where I know how much water goes through our meter at our recycled water pump station, but when I add up all of the reads at the billing meters, and there's 210 recycled water meters right now, that they don't add up to the number that comes out of the pump station. They're less. And why would that be? And what I'm concerned about is that there are some low flows in these larger recycled meters that are not being properly captured, and that means we're not generating all the revenue that we should from the recycle program. So I'm looking at how we're going to deal with that. But aside from just the sizing issue, as the meters get older, they tend to wear, and that's when they begin to under-register as well. So the challenge for water agencies is to look at when is the appropriate time to spend the money to actually replace a meter. And we'll talk about that when we get into O&M, about some ideas about when it makes sense to actually incur cost that ultimately you would recover as you are generating more revenue by a more accurate meter. We get calls periodically about people that are concerned their bill is too high and think that the meter is the culprit, and we try to explain to them that it's usually not, that the likely cause of a high bill is going to be either a leak. It could be just habits and overusage, but oftentimes the culprit is some sort of leak, either on a running toilet, which can add up to a lot of water over a long period of time, or potentially pipe leaks in perhaps their irrigation system or in their yard someplace. Those that kind of say, hey, your meter's got to be the problem, you should replace the meter, tend to be surprised when what really happens is their bill goes up, because the likely problem with a meter that's older is that it's not reading all the flow, and when you replace it, you actually start capturing all that flow, and their bill increases, and then they get all uppity. The explanation simply is, hey, you were getting away for a while without paying for all your water. Now we're asking you to pay for it, which is always an interesting conversation. Talk about where meters are located, especially the billing meters. We've touched on this a little bit on service lines when we talked about where the responsibility transitions. In most cases, especially in Southern California, we're going to see some sort of meter box, likely out at the curb, as you see in this picture, at a parkway. In some cases, they might be behind the sidewalk in a customer's yard. Typically, the water agencies can be responsible for the service line up to the meter, and then the customer is responsible on their side. You can see in this picture, it kind of illustrates some of the things we've talked about before: the water meter, the angle meter stop in a meter box, and then it's actually illustrating a house valve. And I think the better design would be to have a customer side valve in the box as well, so if they do have a leak on their line, there's still a way to isolate it. So these meter boxes, you'll also hear them referred to as meter pits or meter vaults. Again, ideally out somewhere in a parkway where it's within the actual public right-of-way. When they are on private property, there should be an easement. As I mentioned when we talked about service lines, oftentimes there might be a couple feet, 2 or 3 feet behind the sidewalk that is actually part of public right-of-way, even though it appears to be the customer's yard that is reserved for utilities. One of the big things we try to avoid is putting meters in sidewalks. They're out there. I've had to deal with them, but what will happen over a longer period of time is the potential for some displacement where the meter is no longer flush or even with the sidewalk. And oftentimes it's not the meter that's moved, it's the sidewalk that is moved. And when you have a vertical discrepancy or between the sidewalk surface and the meter surface, it becomes a tripping hazard. And for an agency like El Toro, where a very large segment of the population is a retirement community, tripping hazards are a big deal. And we have been sued our fair share of times for issues like that. And again, most often It's the sidewalk that's been moved, but that's not going to change the fact that we get sued. So we are very careful about trying to avoid, and oftentimes have gone and where we found issues, incurred the cost to move a meter to get it out of the sidewalk to avoid those types of issues. As we said before, one of the challenges with meter box locations is accessibility. We need to be able to get to it to read the meter. We need to be able to get to it to replace a meter or do any maintenance on the meter assembly. And of course, periodically we actually have to lock meters off. Once you get into colder climates, you may have deeper meter vaults that we can again try to get the service line and meter perhaps below that frost line. Of course, the deeper you go in a colder climate like that, they can be prone to filling up with water. You could have them covered with snow. So there's challenges either way you look at it. In some cases, the meter may be located in the building as opposed to in the meter box. And again, when we do that, we're likely going to have a curb stop as opposed to the angle meter stop that we've typically talked about. So in this picture, you can see one location for a meter, which is where we've been talking about it, kind of in what would be in a meter box out near Parkway or right behind the sidewalk. But in other cases, the meter might be up in the house. Maybe it's in a basement. Maybe it's in a garage. That can be advantageous in climates where you're prone to freezing, because then you can run that service line below the frost line all the way till it comes up into the location of the meter. So, like I said, basements, garages, sometimes on the side of a building. It does become more challenging when you have metering constructed in that manner. They become more difficult to prevent illegal connections upstream in the meter. So anything that if someone has a long service line that's before the meter, they can tie into it and essentially steal water. So that's a challenge. Again, you'd want to have that curb stop at the property line or in the parkway to allow shutoffs, but it certainly institutes or brings challenges in meter reading if you've got meters that aren't really accessible. So if it's in a building someplace, then we are needing to communicate with the customers every time we need to go read that meter. So the ideal situation in my mind is a meter box that's out at the parkway or near the property line that's reasonably accessible. But again, some of these decisions get made based on specific variables associated with individual locations, agencies, sites, etc. Battery meter installations are simply the concept of manifolding together multiple meters. So for the El Toro Water District, the largest billing meters we use are 2-inch. We don't go any higher than that. So if you need more capacity than a 2-inch meter will provide, we put in multiple 2-inch meters. The exhibit you're seeing here actually shows 5 meters. There's a pipeline comes off the main line. All 5 of those meters are tapped off of it, and then downstream of the 5 meters, they all tie back together into a manifold assembly and go on to feed whatever the customer might be. So some of the benefits of an approach like that, it avoids the need to stock parts for larger meters that we would have very few of. So again, we go up to 2-inch and that's it. If you need bigger, then you still use our 2-inch meter. It allows the removal of an individual meter. So if we have, for example, in this exhibit 5 meters and we need to replace one, the other 4 meters can stay online. We can shut the angle meter stop in the customer side valve and replace a meter without taking anybody out of service. If you have single meters feeding the customer, obviously in order to do that you need to shut down the customer while you do that work. So you've got some benefit there. One of the things that might benefit as well is if you have a very large meter, let's say you got a 6-inch, 8-inch meter, at low flow you're going to have the potential for under registration, where you have low flows through a large meter. If you have a series of smaller meters, then maybe that benefits that as well. I, in all honesty, could argue this multiple ways. The standard for nothing more than 2 inches existed at the El Toro Water District since before I got here 30 years ago. So I get the reasons. Again, I get the idea of stocking meters only up to 2-inch. I think that the low flow issue is, especially with newer meter technology, is a little bit better. But the other thing that you got to consider is I'm not flowing low flows through a very large meter, but I'm also splitting my flows at low flow through the 2-inch, let's say 2-inch meters, if that's what they were. So you're still running low flows through some of those meters. So again, you can debate this, you can argue it both ways. What I really want for you is to understand what a battery meter assembly is and be able to identify it and visualize it when we're talking about it. Installation of small meters, again, some of the stuff ties into service lines. We want to have the ability to isolate our service line, so that's where that angle meter stop comes into play. So it's a service line topic, it's a meter topic, because it's attached directly to the meter. So we call that angle meter stop the curve stop as well. We also, I believe, is a good design to have a customer side valve. That way you can shut your angle meter stop, you can shut the customer side valve, and it allows you to replace a meter. It allows the customer to gain some control over a shutoff if they have a leak within their property. So it's part of the installation that I think is appropriate design. The actual meter connections, a couple different types, threaded. You can see on a small meter here on both the inlet and the outlet you have a threaded connection. That threaded connection is going to mate with what we call spin coupling on the angle meter stop. So you can see the angle meter stop that has the female threads that would attach directly to the threads on the meter. Those are typically going to go up to about 1 inch. As you get to 1.5 and 2-inch, we've touched on the word elliptical flange before. That's what the elliptical flange looks like on the meter side, and then a picture of a angle meter stop with an elliptical flange. So they get bolted. It's obviously a 2-bolt connection with a gasket in between, and that's how you connect the larger meters to the angle meter stop, and ultimately on the customer side valve as well. So once again, you've seen this picture before, kind of bring it all back into perspective a little bit on our positive displacement meters and our billing meters. So we started with our saddle, we have our corporation stop, we have copper piping coming into an angle meter stop, in this case a compression by spin coupling. This meter has threads on both sides. I think it's probably a 5/8 inch meter. And then the customer side valve, which is just a little ball valve with again, spin coupling to connect to the threaded connection on the meter. And then it goes on to the customer side stuff. Hose bib, this is actually a pressure regulator up here. Customer house valve, to be differentiated from the customer side valve in the meter box. So we've kind of taken it from the service line, from the main line, all the way through to the billing meter section. We will move from here to talk about larger production type water meters within the distribution system itself, and then a bit on O&M as we conclude the week 15 material.